right, welcome back to continued discussion on the applications of the normal distribution and assessing normality. Let's talk some more about that Wendy's drive-thru. In fact, let's look at some more probabilities having to do with how long it's going to take you to get through that drive-thru. Let's say I want to know the proportion of the cars that take between 2 and 3 minutes to get through get through the drive-thru. Notice that my question uses the units of minutes, whereas the setup to the problem only gives me time in seconds. So I'm going to have to convert 2 minutes to 120 seconds, and 3 minutes, of course, is 180 seconds. And those are going to show up someplace on this standard normal distribution after I find their z-scores. So let's find the z-score first for the 120 seconds. So z-score for 120, I'll write it down there so I can tell it apart from the other one, is 120 minus 138.5, because that's the mean given up here in the original problem, divided by the standard deviation, also given as original information. And that number is negative 0.637931, but remember our chart only goes to 2 decimal places after the decimal point and the ones placed before it. So our z-score will be negative 0.6, and I will have to round up to 4. That is the z-score for 120 seconds. The z-score for 180 seconds, I will do the same, use the same formula. I'll take the time in which I'm interested, the 180, I will subtract from it the 138.5 and divide by 29. Rounding to the hundredths place for my z-score, I get 1.43. So let's see, negative 0.64 is probably about there, and that is my z-score for the time of 120 seconds. And over here, I need to go out to 1.43, so about right there. And that's for my time of 180 seconds. Now I need to do some more calculating and more thinking about this. So I'm going to rewrite this question here, the proportion of the cars, because the proportion of the cars that take between 2 and 3 minutes to get through the drive-thru will be exactly equal to the probability that a random car takes between 2 and 3 minutes to go through the drive-thru. So for now, I'm just going to rewrite this as a probability. So the cars take between 2 and 3 minutes, which we know is between 120 and 180 seconds. And let me clean up a little bit more, get this out of the way. I think you know that conversion. We don't need to have that there. What we do need to keep are both of the z-scores, though. Our first z-score is negative 0.64. So to find negative 0.64, I have to go lower down here. And there it is, negative 0.6, 0.60, 0.61, 0.62, 0.63. I gotta go still further. 0.64, negative 0.64, gives me the area of 0.2611, the area under the curve there. Okay, so the area for the z-score of 120 is, what did I say it was? 0.2611. And now we need to find the area for the z-score of 180. But that z-score is positive. It's not going to be on this chart. I need to get the other half of the chart. Now we are looking for the area underneath the curve and to the left of the z-score of 1.43. So there's 1.4, there's 1.40, 1.41, 1.42, 1.43. So that is 0.9236, the area under the curve to the left of 1.4. So let's shade in those two areas. The area under the curve less than the z-score of negative 0.64, or 120 seconds, if it were not on the standard normal curve, would be that area. And then our second area would be the area to the left of or below 180 seconds, which has a z-score of 1.43, as we see. So I'm going to shade this, all the area to the left this way. But wait a minute, we're not interested in either of those areas. The area that we are interested in is here. It is the area between the two z-scores. Well, the area to the left of 180 seconds, or 1.43 is the z-score, is 0.9236. That's a larger area. And if we subtract the smaller area from it, let's see, 8, 10, 6, 6, 0.6625 is the area between the two. The area below the larger z-score minus the area below the smaller z-score gives us the area between them. So the proportion of cars that spend between 2 and 3 minutes in the Wendy's drive-thru is 66.25%. And as an added bonus, if you want to interpret that proportion, you could say that out of 100 cars, about 66 of them will wait or spend 2 to 3 minutes in the Wendy's drive-thru. One last question about this Wendy's drive-thru. Would it be unusual for someone to spend more than 3 minutes in the drive-thru? Would it be unusual for X to be greater than 3, or, of course, that means X greater than 180 seconds? We don't have to get rid of everything that we had before. Some of it will be very useful. In fact, knowing the z-score for 180 seconds, or 3 minutes, and the area to the left of that z-score are very important for this, even though we don't want to know what's going on. You know, the percentage of people who spend in less than 3 minutes. We're interested in the people who spend more than 3 minutes. The area under the curve is 1. So if we take 1 and we subtract the area to the left of that z-score of 1.43, we subtract this, so it equals 0.0764. So about 7.6% of people will, or of cars, will spend more than, greater than 3 minutes in the drive-thru. Is that unusual? We consider something unusual if it has less than 5% of a probability of happening. Less than 5% we consider unusual. This is slightly above 5%, so no, it would not be unusual to spend more than 3 minutes at a Wendy's drive-thru. I suggest you spend some time calculating whether or not it would be unusual for someone to spend more than 10 minutes in the Wendy's drive-thru. So the examples we just did were all going from interest in a value of a variable and moving from that to an area, which is a percentage or probability, the area under the curve. Let's talk about reversing the process. If you have the area under the curve, which is a percentile, a proportion, or a probability, find the corresponding data values. For example, Let's say you know that someone scored in the 80th percentile on the SAT in a year when the mean was 520 and the standard deviation was 110. And those values do change every year. So you're talking about a score in the 80th percentile, and the area under the normal curve can also represent a percentile, because we talk about it as percentages, right? So what we need to do is to convert that 80th, which is 80th percentile, to a decimal first. And it's the area to the left of which z-score? Well, we have to use the chart. We're going to use the chart in reverse. Let me pull up the chart first. Knowing that 80 is more than 50%, I have pulled up the top half of the chart, and I'm looking for a percentile. I do not have a z-score. So if I'm looking for a percentile, a proportion, or a probability, I have to look within the body of the chart. So I'm going to start looking for 0.80, or as close to 0.80 as I can get. Let's see, here's 0.7995, and here's 0.8023. So which one's closest? I believe it is this one, because it is only 5 ten-thousandths away from 8, and this is 23 ten-thousandths, so not this one. So that's about as close as I can get to that 0.80. So now what I have to do is read the z-score. Oh, that's interesting. It's 0.8. And the other part of the z-score is the 4. So that is the z-score that corresponds to that percentile. Let's remove the chart. So once again, we started with the percentile, which is an area, and we moved to the z-score. We still do not know the SAT score that we're looking for. We'll use the z-score formula to find it. So when we calculate a z-score, we're looking at the value minus the mean divided by the standard deviation. So in this case, we have the z-score. It's 0.84. And do we have the value of the SAT score that gives us that z-score? No, that's what we're looking for. But we do have the mean. It's written in the original problem of 520, and we have a standard deviation of 110. If we multiply both sides by 110, we have to multiply both sides, because as you do unto one side, you must do unto the other, the golden rule of algebra. That will give us x minus 520 on the right-hand side and 92.4 on the left-hand side. Almost done, not quite. We have to isolate that x to find the score. So if we add 520 to both sides, x equals 612.4. Do we round up? Do we round down? Well, it's a 4, so you'd think we would round down. But if you only score 612, you're not truly in the 80th percentile. So to get into the 80th percentile, you would have to score 613. So that is the SAT score that is in the 80th percentile. So given original data, we have taken that original data from a continuous random variable. We have computed the z-scores. We've found the area under the curve, and we've interpreted that area as a probability or a proportion or a percentile. And then we have also worked from the probability, percentile, or proportion. We've interpreted that as the area under the curve, and we have moved back to the original value. We can calculate in either direction. Now, I would like to show you all of these calculations on Minitab, but I feel like that is better done in person, or as in person as we can get online in Blackboard Collaborate. I will do one more short video on assessing normality. See me there.